Okay, so in manifold theory, what we're interested in is to embed or to attempt to embed a set into some Euclidean space, so that we choose a dimension, say little m, into which we want to embed a manifold M. So essentially, at the end of it all, if we have a way of mapping a set, whether it be a set of matrices, whether it be a set of invertible matrices, or if it is a sphere or some set that is conceivably not Euclidean, the idea is to take every element of that set and write it in coordinate form. So to find a minimal value little m such that we could map every point on a given set into some sort of coordinate system with m coordinates, like so. Okay, so broadly speaking, if you take a set of all, say, 2 by 2 matrices with, say, entries B1, B2, B3, B4, you could in theory map this or rewrite this particular matrix, depending on which order you choose, as having or being equivalent to a coordinate, a vector containing 4 coordinates, like so. So you can regard a matrix in that form, or you can regard it in that form. So theoretically what it means is we can map this matrix into a vector containing 4 coordinates, and this 4 coordinates, of course, is in R4. So if you take the set of all 2 by 2 matrices, if you perform this map, rewrite the entries of the, or at least the matrix in terms of a vector, we could say that the set of all 2 by 2 matrices is a manifold, therefore, because you can embed it in R4. And the dimension being 4, we would say it's a 4-dimensional manifold. So the set is still a set. It contains its original elements, whatever it is, like in this case 2 by 2 matrices, but it's a manifold. It's a 4-dimensional manifold because it can be embedded in the R4 Euclidean system. If we take another example of this type, suppose we take the set of all 3 by 3 matrices in which the elements are of the form ones down the diagonal, zeros below the diagonal, and the remaining 3 elements of this matrix are arbitrary, say A, B, C, real numbers. In this case, there is no need to map this 3 by 3 matrix into a vector containing 9 coordinates as in the previous example. Here, of course, since every matrix in this set would have the same elements down the diagonal and below the diagonal, we need only map this to the 3 vector ABC. So this is in R3. So even though this set of matrices contains 3 by 3 matrices, every matrix could be uniquely mapped to a vector in R3. So a set containing all matrices of this type, where ABC are arbitrary real values, can be embedded uniquely into R3. So we would say that this set here would be a 3-dimensional manifold. It can be embedded in a coordinate system containing 3 vectors in a 3-dimensional Euclidean space. Now, a classic example of a system that's at least one of a set that's already a subset of Rn, where we could map that system into a lower dimension is the sphere of any radius. Let's suppose even if the sphere is of radius 1. So you take a sphere, and this is a classic example of this type, right? We could take every point on the sphere and map it to, in a particular way, onto a plane of that type. And the manner in which we do that is the following. So if this is the north pole of that sphere, we run a line from the north pole through the point that's on the sphere. Remember, the point is that point there, and we end up with a mapped point in R2 in this plane. So if we choose another point, we would map this point via the north pole. So the north pole, the line starts at the north pole through the point on the surface of the sphere and map this onto R2. And we can do this for every point uniquely on this sphere. So even though the sphere exists in R3, right, we can map every point on the sphere onto this plane, which is in R2. So in other words, the sphere can be opened up. This sphere can be opened up into this plane. So the sphere, although exists in R3, actually is a two-dimensional manifold. So therefore, this sphere can be a subset of R2. It's then what we say, a two-dimensional manifold. If we go back, so in each of these cases, the set of all 2 by 2 matrices there, this set would be a two-dimensional manifold. Right? And the set of all 3 by 3, this is incorrect. Let's erase that. I said it was actually a 4-dimensional manifold due to this R4 there. So that's a 4-dimensional manifold. And this second set of 3 by 3 matrices having the structure that I spoke about here, this would be, let me do that in a different color. This set would be a 3-dimensional manifold. Okay, so that, broadly speaking, is what we would define as manifolds. If a set can be mapped into a subset of Rm for some minimal value m, we say that that set is an m-dimensional manifold, i.e. it can be embedded in a subset of Rm. So for this we need a formal definition, and the classic formal definition will be given below, but keep in mind that the idea expressed above is essentially the important aspect, and that is what we're interested in when we're dealing with manifolds. So let's have a formal definition. So suppose we have a set M. This set could be the set of 2 by 2 matrices. It could be the set of 3 by 3 matrices of a specific structure I mentioned above. And let's take some subset U alpha of this manifold. Let's take another subset, say U beta of this manifold, and what we defining is a map, let's call it map, that maps this subset, let's call this map Chi or Chi alpha to a set V alpha, and V alpha is a subset of Rm. So what you got here is that's your manifold M, and this is your Euclidean space Rm. Right, and we have a map Chi beta, and I'll give the properties of these maps below, that maps U beta to say V beta equivalently. Now, what are the requirements? First of all, let's put this. So the definition then says an m-dimensional manifold, an m, small m, that's the same m that comes from there. So an m-dimensional manifold, right, is a set together with a countable collection of subsets. M-dimensional manifold is a set with a countable collection of subsets U alpha, with a countable collection U alpha, each one being a subset of M, right? And one-to-one onto maps chi alpha or chi alpha, right? That maps these U alphas to V alpha, and the V alpha is a subset of Rm. That's important. And these maps satisfy certain properties. That satisfy the following properties. Okay, one is that the U alphas cover the set M. So one, that the U alpha, at least the union of all the U alphas over the alphas equals M. The second property is that on the intersection of U alpha and U beta, this map that works on the intersection, so it's the map that is the inverse of the chi alpha. Remember, the inverse exists because chi alpha is 1-to-1, and this composed with chi beta, and I'll give a little sketch of what actually is going on. This map is smooth in the usual sense. So let me just describe what's happening as far as these maps are concerned. So if you look at chi alpha inverse, so we're concentrating, of course, only on the intersection, so let me indicate what's happening here, right? So this little section would be mapped by chi alpha there, and it would be mapped by chi beta there, right? So there, if you take the inverse map chi alpha, so you, on that little section there, if you take chi alpha inverse, it goes now in that direction onto the intersection. It's an onto map, so it blends back into the intersection, and from there you get chi beta acting on it, and it leaves it down here. So you've got chi alpha inverse going that way, and then chi beta taking that down there. So that's the map we're speaking of. And that is in fact the region that we're speaking about here. So in that little section, let's suppose that the map chi alpha inverse composed with chi beta is smooth. And thirdly, what we want is that the space is Hausdorff. So M is Hausdorff. Again, in your classic definition of Hausdorff. That is that for every point in the set, you can find a open set which does not intersect with an equivalent one for the next set. So that's the formal definition of a set being a manifold. But keep in mind that what this boils down to is that if you can embed a set in Rm for some minimal value m, we have an m-dimensional manifold, and think of these two examples, and particularly the interesting example of the sphere. Now, in the context of this definition, we will revisit the sphere example. In other words, we need to set up the maps and so on. This is not always the easiest thing to do, but let's now consider the set S2, which is the set of points x, y, z, for which x squared plus y squared plus z squared equals 1. So this is your circle of your sphere of radius 1 centered at the origin. Right. We're going to define the open sets, or at least we're going to define the equivalent of the U alpha, U betas in that definition. So first of all, we will say let U1 be equal to the whole of that sphere excluding the South Pole, or rather excluding the North Pole. Let's do it in that order. So this point 0, 0, 1 is the North Pole. U1 is the whole sphere excluding this point. And let's suppose U2 is S2 excluding the South Pole. It's clear that U1 union U2 gives you your whole set S2. And we now have to define these maps. So and let's suppose chi1, which is going to be mapping U1 to R2. Let chi1 of x, y, z, and of course here x, y, z belongs to U1, be equal to a point in R2 with the forms x over 1 minus z, I guess. And the second coordinate is 1 minus z2. That's 1 minus z. This would obviously be in R2. So chi1 goes from the set S2, or particularly from U1 to R2. Chi2 is a map that x on U2, and that will have the coordinates x over 1 plus z, y over 1 plus z, and that 2 is in R2. So chi1, chi2 goes from R3 to R2. In particular, it's clear that chi1, we are saying, goes from U1 to a subset in R2. Chi2 goes from U2 to a subset in R2. So based on these definitions of chi1, chi2, U1, U2, we can show that the S2 is in fact a two-dimensional manifold. And just for completion, we can show very easily that chi2 inverse composed with chi1 is in fact equal to x over x squared plus y squared, y over x squared plus y squared. So the chi's satisfy it can be shown satisfies the properties of defined in the definition. And therefore S2 is a two-dimensional manifold. Right, so another example, which I'm not going to go into the details, is that your torus, your donut, is also a two-dimensional manifold. You can say that the circle generated in that direction provides one of the dimensions, and the interior circles, the cross sections, provide another dimension, and that gives us the two dimensions. This, of course, relies on the property that the circle is in fact a one-dimensional manifold. So using this idea, each circle having a one-dimensional manifold, we have a two-dimensional situation in that previous donut torus example. Here, of course, it is just the circumference of the circle we're talking of. So it has a dimension of 1. It's clear that if you take the circumference, you can open it up into a straight line, and a line is of dimension 1.